Okay, I just want to spend a brief amount of time talking about display systems and electronic images, and and we'll get to a big takeaway here. But it largely is we need to understand how these monitors work in order to better understand how we're viewing the images and any problems that might result just from viewing them on certain monitors. So here's some objectives, pretty brief, but we're going to talk how these LCD monitors work. We'll compare and contrast them a little bit with cathode ray tubes, which is like kind of old school, the non-flat panel types. Then we'll talk about the different characteristics of monitors that affect the image display. And the big thing is we're driving to describe how these modality workstations function, and particularly compare and contrast like the workstation monitor with what the diagnostic viewing monitor, the ones that the radiologists are using. So the chapter does a great job of discussing how LCD, and I should also add LED, LCD monitors in here, how they function. And there's some key terms here that I want to kind of highlight real quick. The first is going to be polarized, and he gives a definition of polarized on page 613. He says polarizing sunglasses work to reduce reflective glare because the plastic in the lenses contains long, slender, aligned chains of iodide molecules which act somewhat like a radiographic grid. So only those light waves whose electronic component vibrates in parallel with these long chains of molecules can penetrate through, and the light waves vibrating in all other directions are blocked by the molecular grid. So the LCD monitor is going to use two polarizers on it, one on the top and one on the bottom, and between those polarized glasses, there's going to be a TFT array, or perhaps the TFT might be on the other side, just depends on the manufacturer. But the critical component here is this liquid crystal that's sandwiched between it. And this is a pneumatic liquid crystal, so that's our other key term here. Pneumatic liquid crystals that are sandwiched between these two polarized glass layers. And the crystals are actually going to twist certain lights, wavelengths, and not twist others. And it depends on what the TFT array tells it to do. But it may activate the crystal and cause it to twist, for example, this light ray, and so that it's emitted through the monitor screen. In other light rays, it might not twist, and so this one's not going to come through. And this is basically how an LCD monitor functions. So let's consider the old school, the cathode ray tube monitors versus LCD, because you still might see some cathode ray tube monitors out in the clinical site. And the easiest way to tell the difference between the two is just to look at them in profile. Cathode ray is going to have kind of a big fat back, and a lot of times it's got a slight bulge to the tube. Like that, and so this is the viewing surface here, versus an LCD is going to be a flat panel thing with a little guy that comes down like that. This is typically how the difference that they look in I'm sorry, this is a terrible drawing of a stand. This is typically how they look in profile. So this guy over here is going to be pretty heavy. It's got an actual electron gun inside here that's producing the images, whereas this guy, like we've discussed, is using just some thin film polarized glass. So the differences between these two is luminance is actually going to be higher in the center for the CRT, and so that's going to mean it's less uniformly bright. Whereas LCD is uniformly bright, and it also tends to maintain a uniform sharpness of detail. The CRTs, one of the things that does make them good is they're very durable, right? And they have better color reproduction. But that will change some over time. And the big thing that we're having, the big draw of LCD that drove our push to them is increased spatial resolution. So let's talk a little bit about this resolution and the display characteristics that go into making it possible. First of all, we've talked a lot about matrix size, but monitors also use the matrix, and so as the matrix size increases for the monitor, so will spatial resolution. The other thing that's important, again, is pixel size, and so as the number of pixels per square centimeter increases, so as pixel size decreases, the number of pixels per square centimeter increases, and the monitor is going to be able to display radiographs in a higher resolution. Of course, this costs a lot more, but it's going to give us better resolution. And the way that we talk about that difference between the pixel sizes, we're going to use the term pixel pitch. And if we were to imagine pixels, now we know at this point in the game that pixels don't actually have a real size or a shape. They're just supposed to be dots. But for the sake of this drawing, let's draw this. This is what pixel pitch is. It's the distance from the center of one pixel to the center of another pixel. We might also call this dot pitch. And it's going to determine the sharpness of the image. Of course, the closer the pixels are together, the sharper the image. So that may seem a little bit vague, so let's go ahead and represent that and get down to just a little bit more depth with it. And like I said, LCD monitors have a higher resolution than the cathode ray tube, and that resolution is going to be determined by pixel size and pixel pitch. The ACR has actually made a determination on what the spatial resolution should be for diagnostic monitors, and they said at least 2.5 line pairs per millimeter when viewing a 14 by 17 inch image. And just so that you understand the significance of how important it is to have good spatial resolution, I've included this chart that moves up from a matrix size of 1 by 1 to a 100 by 100. Just in theory, that's what the matrix size of these images are. So we also have talked quite a bit about contrast resolution. It's a significant thing too, and it's apparent there in our monitors. And the best way to talk about it is it's the difference between the maximum and minimum luminance of the display. So for the purposes of monitors, the contrast resolution is going to have a lot to do with this maximal luminance property, and that refers to just the monitor brightness. So the ACR standards specify that for grayscale monitors like what we use, it needs to provide a 171 candela per square meter luminance. Now, what has us beat on luminance, and will always have us beat on luminance, is of course the old film boxes. Those light boxes have like a luminance of 1,000 something, right? Candela per square meter. So they will always be brighter than our monitors. And that was just the reason that we use those monitors. In fact, mammography, the old mammography film boxes had to be like 2,000 luminance just in order for us to have appropriate luminance for what we were viewing. The other thing that I think is important, very, very important to contrast resolution, is the grayscale. So to accurately display grayscale, the display monitors must be at least 256 shades of gray. Now what's interesting about this is in this color depth and bit depth type thing is we have a bit depth that goes much further than that on almost all images that we've looked at. And so we've talked about this. The reason why we can get away with this 256 shades of gray is that's far more than the 16 shades of gray that my eyes can see. And even though the image data might have 2,000 shades of gray within its bits, we can just window and level appropriately and then pull out that added contrast resolution that's there latent in the data. Now, all of this builds towards noise, because that's going to be the thing that deteriorates or takes away from our display resolution, our contrast resolution, spatial resolution. So display noise is just monitor noise, any monitor noise that's visible on the finished radiograph. So you spilled some white out on the monitor, or someone's poked the monitor screen a whole lot and we've got that weird little rainbow colored spot off in the corner, or like every other smartphone that you see out there, it's cracked. Whatever has caused an interruption of the polarized surfaces there could damage our ability to see what we need to see on the radiograph. So it's important to know, okay, is that monitor noise? Is that noise on the image coming from the monitor? Is it a glitch with the way that my computer radiography reader is working? Where is that noise coming from? And almost every monitor you'll work on at some point will have some kind of problem that comes from just the monitor itself. And the ways that we typically think about this in terms of monitors is spatial noise. And so this is caused by phosphor-granularity, and so there's going to be these random luminance variations. And again, that is from poking the monitor screen a lot of times, or the monitor screen maybe at one point in time being in a freezing cold condition or a burning hot condition, something that's caused the random luminance. Another temporal noise is this is the electron beam intensity as it fluctuates in the back and forth in the back of the phosphor monitor. A lot of times we cannot perceive this, the human eye cannot perceive this, but I always think about, if you're ever watching the news and they're filming someone sitting in front of a computer screen, a lot of times the camera that they're using to film can see this temporal noise. They can see the scan frequency on the monitor that's being filmed. And so that feedback loop just kind of speaks to temporal noise that eventually if this is apparent, we would want to think about getting a new monitor. So let's talk some about some of the terms that help us better discuss that temporal noise thing. And one of the things that he points out in the book is that this is all centered on response time, and this is page 615 in our textbook, that however quickly this monitor is responding to the data that it's receiving, that is basically the time necessary for a pixel to change in its brightness. Now this refresh rate or refresh time is the time that it takes the monitor to then reconstruct the next image that is being projected. And then the term persistence, even though it's not included in our textbook, I think it's helpful to think about the term persistence because there can be a time when the light emission from the phosphor, especially on a CRT thing, or even with LCD monitors, there can be image persistence, and this is going to be called image retention. And this is the reason why we use things like screensavers on our monitors to make sure that we don't have an X-ray image that just hangs out up in the crystals, always being projected there, kind of ghosted over the other images that we're trying to view. So, of course, as I've hinted at, there's always going to be these weakest links in the way that we work with digital technology, and he does a good job of pointing out in this conclusion that whatever the weakest link is, it's going to be what finally limits the image quality that we have displayed in front of us. So this is why the radiologists use a Class 1 monitor at their diagnostic workstations, and also why those monitors are so expensive. And so we need to be careful when we're looking at the images on the Class 2 workstations that we don't think that is like the final image. So this difference in resolution, the difference in contrast resolution, all of those whatever may be suboptimal about our image, as we're looking at it on our Class 2 workstation, may be much more apparent on a Class 1 workstation. And so whenever a radiologist has a question about an image or sometimes it's best to try and view it on their monitor if at all possible, so that you can see exactly what they're talking about, because again, they're going to have the better image the better monitor for viewing what we're trying to see. All right, thank you, and bye.